Hello and welcome to our video presentation. Today we will give you a presentation about our topic, which is metallic bonding and band theory for our subject, which is Chemistry 361.
So this is our group members. First one Adam Mulia bin Zainuddin, Muhammad Faris Azim bin Zamri, Arif Farhan bin Muhammad Adnan, Muhammad Ikram bin Muhammad Nasir, and the last one is Aizam Yusuf bin Ishaq.
And this is our table of content.
For objectives, define metallic bonding and explain how metal atoms are held together by a lattice of positive ions and delocalized electrons. Next, describe the sea of electrons model and relate it to the physical properties of metals. Explain key properties of metals such as electrical conductivity, thermal conductivity, malleability, ductility, and luster in terms of metallic bonding. After that, introduce band theory and distinguish between valence band and conduction bands. Explain how electron band structure accounts for the electrical conductivity of metals. Differentiate between conductors, semiconductors, and insulators based on gap concept. Lastly, relate metallic bonding and band theory to real-world applications such as wiring, electronics, and alloys.
For the first one is introduction. Metal are widely used in daily life because of their strength, shininess, and ability to conduct electricity and heat. These characteristics are mainly explained by metallic bonding, where metal atoms release their valence electron to form a shape pool of mobile electron around positive metal ions. This delocalized electron cloud allow metal atoms to slide over one another without breaking the bond, giving metal their malleable and ductile nature. To further describe the movement of electron in metal, band theory is used. It states that the valence and conduction band in metal overlap, allowing electron to move freely and resulting in high electrical conductivity.
For the first one, which is finding and discussion, which is for metallic bond. Metallic bonding occurs when positive metal ions are arranged in a lattice and held together by a sea of delocalized valence electron, allowing the electrons to move freely throughout the structures and giving metals their characteristics properties such as malleability, ductility, metallic luster, and high electrical and thermal conductivity. Band theory further explains these properties by showing that in metals, the valence band overlaps with or is partially filled with the conduction band, enabling electrons to move easily under an applied electric field, which result in efficient conduction of heat and electricity, and highlights that mobile electrons are the fundamental reason for metallic behavior. Okay. For the example, which is metallic bond in magnesium is stronger than in sodium due to magnesium having two valent electron and smaller while sodium only have one. Okay. For the next one, for finding and discussion, which is electron C model. The electron C model explains metallic bonding by describing metal atom as positive ion arranged in a regular lattice, surrounded by a sea of delocalized valent electrons. These electrons are not attached to any one atom and are free to move throughout the metal structure. Okay. For the second one, the strong electrostatic attraction between the positively charged metal ions and the mobile electron hold the metal together because the electron can move freely. Metals are able to conduct electricity and heat efficiently. This model also explains why metals are malleable and ductile, as the layer of metal ions can slide past each other without breaking the metallic bond. Okay, for the next one, for finding and discussion, which is the third one, which is band theory of metals. which is the theory the localized electron move freely through band formed by overlapping molecule orbital. For the first one, which is band theory, explains the electrical properties of metals by describing how atomic orbitals overlap when metal atoms come together in a solid. Instead of having discrete energy levels, the electron occupy energy bands, mainly the valence band and the conduction band. For the second one, which is in metals, the valence band is either partially filled or overlaps with the conduction band, allowing electrons to move freely under an applied electric field. This high mobility of electron is the reason metals are excellent conductors of electricity and heat. Band theory also have explained why metal reflects light and have high thermal conductivity. Okay, for the next one, which is we have an example, which is you can see at the picture, which is we have three, which is insulators, semiconductors, and conductors. For the first one, which is insulators, insulator have a large band gap, so electron cannot move freely, and electrical conductivity is very low. For the second one, semiconductor have a small band gap, allowing limited electron movement when energy is supplied. Okay. For the third and the last one, metals or conductors have overlapping valence and conduction bands, enabling free electron movement and high electrical conductivity.
Moving on to number 4, which is doping. Doping is the process of introducing small amounts of impurity atoms into a metal or semiconductor to modify its electrical properties. In N-type doping, extra electrons are added, increasing conductivity, while in P-type doping, holes are created to allow electrons to move more easily, as shown in the slide. Doping affects the band structure by introducing new energy levels near the conduction or valence band, making it easier for electrons to flow. In metals and alloys, this process can also fine-tune properties such as resistivity, strength, and corrosion resistance. So for our final part, which is semiconductor. Semiconductor are materials with conductivity between metals and insulators, with the common one being silicon. Semiconductor are also split into two, which is intrinsic and extrinsic. Intrinsic semiconductor are pure semiconductor where conductivity depends on the temperature. Meanwhile, extrinsic conductor are a doped semiconductor where conductivity controlled by impurities. So some of the common electrical uses for semiconductor including diodes, transistor, and memory cards, as shown in the slide. Heading on to real world application. So we have many of them. And for example, we have wiring. So how does it work? Wiring works when metallic bonding provides delocalized electron. So metals such as copper have an overlapping of valence and conduction band that allows electron to flow. So this will allow a high electrical conductivity for power and household wiring. For the next one, we have electronics. So it works just like wiring. Metals have no band gap, so electrons flow freely. Meanwhile, semiconductors have small band gaps for controlled current. This will enable transistors, chips, diodes, and electronic devices. And for the last one, which is alloy. So in alloy, metallic bonding allows different metals atoms to meet in lattice. So when this happens, bands start to change will alter the strength, hardness, and conductivity. So alloys are mainly used for stronger structures, corrosion resistant, and tailored materials.
For the last one is conclusion. In conclusion, the unique properties of metals such as strength, malleability, and high electrical and thermal conductivity can be explained by metallic bonding and band theory. The presence of delocalized electrons enables metals ions to remain bonded while allowing layers to slide and electrons to move freely. This combination of structural flexibility and electron mobility is what makes metal so useful in everyday applications. from construction materials to electrical wiring.
So this is the reference that we use for our video presentation. That is all from us. Thank you.